Well, thank you very much to come as many participants to this second webinar organized in the frame of the Woodrise Alliance. I am Frederick Stat, working at FCBA. I'm the boss of Jean-Luc. As a matter of fact, the boss of Jean-Luc. I'm at FCBA, I'm Timber Industry Construction Director. And also, as you know, because FCBA was quite a lot involved in Woodrise story, along with FP Innovation and the BRA colleagues of Japan. So I'm also the coordinator of the Woodrise Alliance. And so we had a meeting in last October, a general meeting. During this meeting, we have of the 24 members of the Alliance all over the world. And we did decide at that time to organize webinars. This one is the second one. And we are very pleased to have you so many, almost 50 participants to discuss about acoustics of tall wood buildings. And of course, I want to thank you, everybody, to be here. Also to thank Jean-Luc Kouyumji, who was the coordinator of this webinar, and along with the people who make a presentation. So Ling Hu, very pleased to have you. We don't know each other, but I heard of you through Jean-Luc, Sylvain Ménard, Sylvain Gagnon. So very pleased to have you here and to hear you and about your work. Catherine Guigou, bonjour Catherine, from CSTB. CSTB is also a member of the Alliance. Thank you to be faithful to what we do here in the wood construction. Also Claes Ackberg from Ackwood, Sweden. Thank you, Claes, for your contribution. And Jean-Luc will conclude the webinar. Jean-Luc, it's yours.
Thank you very much, Frederic, for this introduction. So exactly, we are going to have everyone something like 15 to 20 minutes of presentation, and then the floor will be open to everybody because it's this webinar is open for discussion. Everybody is going to share his own experience. So we will start with Lynn, that is going to share her experience about calculating and predicting performance of impact noise on wooden building. Also, we will talk with Catherine. Will talk about building systems, mainly floors. Some study that we did together, and some results, very fresh results that are arriving just now. Coming from Adif Bois. Then Claes is going to give us a very nice feedback from the field. Claes is working in building acoustics since years, and he has his own company, Ackwood. It's already 2 years. He's running this company, and before he was doing the same job, but for a big institute. Okay, and I will talk about the new facility that we are building now in FCBA for flanking transmission measurement for high-rise building. So I hope this will give a nice picture of what we are doing in acoustics for high-rise buildings, and after that, we will be very happy to have your questions, and we'll be very happy to listen to also your experience, because we know that all around the table we have so many experts. We can organize other webinar on acoustics, no problem. And we know that the experience of everybody help us in preparing and managing very big projects using wood in a very perfect way for acoustics behavior. Okay, now I'm going to give the floor to Lynn, but I'm going to keep in hand the sharing of the presentation. It's very slow. I don't know why. Oh, here. So Lynn, if it's possible for you, I will cut down my microphone. So.
Okay. A noise. The noise. Very much noise.
Yeah, you can start, Lynn. Maybe
Okay.
Jean-Luc, you can ask everyone to put their mic on mute just in case.
Okay. Okay.
You can
so,
start, Lynn. We can hear you.
Okay. Thank you, Jean-Luc, for the nice introduction. Hi, everyone. I'm going to share some of our findings from a preliminary study on some key parameters other than mass of the insulation material and the components of wood wall and the floor assembly to control noise transmission in wood buildings. Also, we found those parameters have been often ignored in producers' specification in our theoretical work modeling and our design. Sometimes we actually, the people called us, the designer and the producer, what the parameter properties we should produce. We should select the insulation material to build a better some insulation material, make a better components or the assembly. So this is what my purpose for this presentation. We like to call the attention, all the research, acoustic research community, pay attention to fundamentals of the wood construction noise control. The fundamental, I call it like the constitution equation, how the material and the components acoustic property correlated to the wall and the floor assembly, the total sound insulation performance. So this is what our attention. So now let me tell you a little bit about who we are. We are FP Innovations, Forest Products Innovation in Canada. Our mission is to serve industry through innovations, adding values to wood products. We have three groups: forest operation, resource, transportation, forest transportation is one group. Second one is pulp paper. The third group is wood products and the building systems. This is what I belong to. We develop innovative building products and the system, code understands solutions to ensure consumer satisfaction and the market acceptance to wood buildings, and make the industry, of course, should be profitable. So I'm working on vibration and the noise control of wood construction. Actually, I really feel very lucky and blessed to work at FP Innovations, because the advantage of working at FP Innovations, because FP Innovation is a research organization with multidisciplinary groups. So we have good multidisciplinary collaboration. For example, when I need or see some needs from the industry, from the producer, from the design, they ask for better sound insulation material or the components. Then what actually I can ask my colleague, material colleague, to develop all kinds of insulation material. We can't find it in the market. Then furthermore, all of those material, innovative material and the property we study, then we go further, build the floor and the wall, then we establish correlation, really made us, the research, a little bit, can see a little bit some answer from my first introduction, the slides. Why we now the next one, Jean-Luc, can you move to next one? Because I like to explain why we study the parameters of insulation material and wood building components. Because this, as I mentioned before, we often have been asked to provide the guidance for the producer and the designer, how to select the insulation materials and the components, what are the parameters I should looking for, or I should, for my acoustic wall and the floor design, or for my products development. So therefore, as I wrote on this slides, what we see the need. We need the guidance or tools for development, the solutions. And specifically, wood industry needs practical solutions for wood building noise control. So let's just move to next one. Jean-Luc. Okay. So, however, we also found noise control for wood construction actually is a challenge, not so simple. So far, according to my knowledge, maybe it's limited, maybe you should correct me. I found all the theory, whatever the equations, work for homogeneous plate, like a concrete slab, maybe works well, but not really for wood. Because wood has lightweight nature. We found only mass law doesn't work. Secondly, even we talk about mass timber, very close to concrete slab, but mass timber is not homogeneous. So whatever those theory still doesn't work for even the mass timber slab. Then the more challenge is what actually in North America, the biggest market at this moment still is the light frame construction. It's really economic, it's the most construction and cost effective system. But look at this system. As shown on the screen, on your right side, on the top, it's the typical North American light frame wood building. We use wood truss or I-joist to make the floor. Now look like a ceiling in this photo. But the detailed construction about the joisted floor system, you can see on the bottom of the right corner. So the floor system is hollowed, made with I-joist or truss or lumber. Then you have the cavity. Then we have topping. We have many layers. Then underneath we have gypsum board. Then under resilient channel. So this is the so complicated multi-layer hollow system. Then the wall is the same. So on the top of the slide, you see the wall, the stud wall, so wood stud wall. So covered by gypsum board for fire protection. But basically similar as the floor system, it's the hollow with air inside. Then we have insulation material inside. Then we have the stud. Then we have the two side with so-called plate. So in such a system, we really have many questions. Now let's move to next slide. Let me just narrow down the challenge as I see the question. So how? We really don't understand the air in the cavity, in such a hollow floor and the wall, wood floor wall system. What the air plays the role? Because we have so interesting observation. Once we have one single large air space, we got a better some insulation for the wall or the floor. Then if we divided this large air space into smaller air space, we will get worse sound insulation performance, the same floor and the wall system. Why? What is the equation we can apply? Or anyway, so this is the first very challenge. For me, I still no clue. Second question, maybe it's easy to do it. This is what we started. Static airflow resistivity of insulation material in cavity. What their role perform? Sometimes sometimes when I talk to non-technical people, I like to maybe simplify this terminology. For people, maybe couldn't picture what does it mean, static airflow resistivity. But simply, I just tell them this is, you can make them similar as like electricity resistance. We simply tell people practically use some not very good name, but forgive me, I like to call static airflow resistivity is sound resistance. It's actually is that. We can have an equation describe the pressure equal speed multiplied by static airflow resistivity. Since this is simply, in my case, I feel people can understand what does it mean. But however, we don't know. What the static airflow resistivity of insulation material related? What is the constitution equation related to whole wall and the floor sound insulation performance? Unknown. Dynamic stiffness of insulation material between layers. Probably this one, I see more literature, more data. Seems people gradually understand. And we also see, especially in European products specification, they put this data in. But how to apply this data in the design? Where is the criteria? We only saw, only in the South Korea building code, they specify a criteria. Say, dynamic stiffness of insulation material should not be larger than 40 milliNewton per square meter. But anyway, we have to verify and see. Actually, it's still too high. I will show you later. Then go to the next one. For me, this just one sentence I can find in the literature. No data, but it's so true. This is what we found. Torsional rigidity, how the wall stud torsional rigidity correlated affect the wall sound insulation performance. We understand the stud joist plays a role in the floor and the wall system. For me, just like a sound bridge, very similar to thermal bridge. Then we need to develop criteria. What the torsion rigidity reach to which value? That bridge is totally connected to gypsum board, then no insulation function at all. However, all of these questions lead us this study, but just the first step. We just started establish our material laboratory. However, our objective, I call the preliminary study, try to identify what are the key parameters and how they affect the sound insulation performance of wood buildings, focusing on dynamic stiffness, static airflow resistivity, and the torsional rigidity. Okay, next slide. Okay, so our approach is quite straightforward, simple. I didn't wrote here just for simplicity. First, of course, we measure the stud torsion rigidity, then the insulation material, airflow resistivity, then dynamic stiffness. Then we built this two-story, 4 units, very conventional North American, just like the apartment building or condominium. Of course, it's very simple. So we have up and down a pair of units on the left photo, on the left side. So we have the complete up and down a pair of room. So we can conduct the flow impact sound and the airborne sound insulation study in this up and down setup. Then we also have a pair of rooms on the bottom. On the first floor, we have 2 rooms. Then we have our wall test facility. Then in the corner of the upper, we have an open 4th unit. This is the open area. This is just for simply screen various of combination of flooring and the finish and the underlayment and the topping. See what the dynamic stiffness plays a role, but it's very cheap and easy to do. It's not very accurate, but if we can do everything on the same facility, use the same approach, we can compare apple to apple. We call the screen study. Okay, now let's move to second one. Next slide, sorry. Okay, so what are the specimen we built? Actually, we built more than what we listed. Or just to show you a few examples. So we built I show you 5 floors in 2 groups. One is mass timber CLT floor. So this specimen is specified to study how the various of underlayment insulation material under the concrete topping affect this floor impact sound insulation. So we used 3 different types of insulation resilient layer. One is wood fiber board. This we quite use in Canada often. It's not the great one, but the cheapest one. It works. Then we use the felt. It's made actually recycle cotton. Then we also have FP Innovations, bio-based non-woven wood fiber mat invented at FP Innovations. Then we also have several lightweight joisted floor. Then we also keep the floor structure the same, keep the finish the same, only change the underlayment between the concrete and the structure floor. Same, we use wood fiber board and the recycled rubber mat. This, we measure those insulation material dynamic stiffness, then we try to see the correlation, how the dynamic stiffness correlated with the impact sound insulation. Okay, next one. So next one is, oh, sorry, too fast. So let's just go back one slide. Okay, now we built several walls. Here I also just show you 2 types of wall for 2 purposes. The one is a box, very simple. Just have the 4 edge, then on the top and the bottom, just a very thinner HDF plate. The purpose for this box, we just change all the filling inside, the sound absorption material in the cavity of the box. We try to see how the airflow resistivity affect this box's airborne sound insulation. So actually we did more materials, the filling materials, absorption material for the cavity, but I just show you this 3 significant one. The one is fiberglass. Everyone knows it's very common for every country. Then also rock wool. Then we also use the wood fiber board, but maybe nobody really used the wood fiber board. Then you will see some interesting results. Then we also have the real wall, wood frame, wood stud wall. So the wall group number 4 to 7, actually more than that. We did more than 10. However, for this wall, we only change the stud. This is the advantage. We can't get all kinds of studs with various of torsional rigidity in the market. So we ask our colleague to develop all kinds wood-based stud. We call the composite stud with various of torsional rigidity to help us do study. So, okay, now next, so very quick, now we just see the results. So the method, okay, just a very conventional, okay, just a very conventional method, whatever instant. But we use ASTM, not ISO. But some ASTM are very similar to ISO. So let's just go. Let me quickly show you results. Okay, let's go. Next, results. Okay, the results, obviously for dynamic stiffness, you see, we, of course, because we measured is not in the tradition, not in the acoustic chamber, actually in the mock-up. So we measure actually is apparent impact insulation class, AIRC. So obviously you see the correlation. Once you have the lower dynamic stiffness, we got a very high AIRC. So this conclusion, the trend applied to both mass timber floor and the light frame floor. Okay, now next one. Next one, I wanted to show this, for me is very exciting one. I really like it. This is what we've discovered for the stud wall, how the apparent sound transmission class, ASTC, correlated, so well correlated with the stud torsional rigidity. This is easy to understand. When the stud is flexible, measured, indicated by the low stud torsional rigidity, it means we decoupled the two gypsum board. So the sound bridge effect is very lower. When this rigidity is very high, like the solid lumber, solid timber stud is very high, the torsional rigidity, very stiff, then the stud just form the direct sound transmission bridge. That's it. All the sound just goes directly. Even in this case, we recognized whatever you put the sound insulation material in the cavity, waste money, because all the sound just directly through the stud goes to next room. They don't bypass the cavity, very little bit. So waste investment. We told the people, if you use such a stud with very high torsion rigidity, forget it, or the insulation approach, you know, this and that. Okay, then next one is the last one. Last one is, we just, this also probably for you surprise. So some people ask me, okay, look, with the fiberboard, the static airflow resistivity is so high, then compare with the traditional, whatever we are using, fiberglass, with the rock wool, the sound insulation performance is amazingly high. You see 5 points. Yeah. Now, of course, now I just answer your question. Then people say, okay, I don't really think like that, because they say, okay, with the fiberboard is dense, then the fiberglass and the rock wool. Yes, but this is not the only one. This is not the mass, because we also have another data. We put the felt with the aluminum film. So for the felt, in this cavity, even lightweight, but we achieve very high ASTC. For those type of felt with aluminum on film coated, actually the static airflow resistivity is infinity, because actually the pulse for this such type of material almost is 0. So very high, is much higher. We got 36, lightweight. So this is why I always like a challenge for light frame wood construction, even for wood construction. Only mass load doesn't work. Many other things we have to look at. Okay, now final conclusion. Okay, so what is the conclusion? We say, of course, dynamic stiffness and the static airflow resistivity of insulation material and the stud torsion rigidity significantly affect the sound insulation performance of wood assembly. They are very important parameters for noise control, wood wall, and the floor design, modeling, and the products development. Okay, so almost finished. Last one, I really thank for wood industry and the Canadian government or our colleague to support financially, mentally, technically for this study. Okay, so last one, the next step. because we just at the beginning. Then we try to establish our material laboratory by equipment to measure more torsional rigidity, and measure more dynamic stiffness, even the impact force. We going to buy force plate, we will buy airflow resistance meter, we will measure more, we will try to see more correlation this moment before we can get theoretical understanding. At least we try to establish some empirical correlation equation. We will see. Okay, thank you for your patience, for your listening. Any question?
I think we are going to keep the question for the session at the end of the session, and then we will get all question for everybody. Is it okay for you, Lynn?
Yeah, no problem.
Then we can move to the next presentation. So I have to stop my sharing because somebody or Catherine, you have to. Okay. Oh.
So our next presentation is concerned with wood floors and the low frequency impact noise aspects. And most of these, we were going to talk about different studies that we did, and most of them were carried out by CSTB, myself, Jean-Luc Ouyongji from FCBA, and also Nicolas Balanin from CERCAL. And also with another big group, which is the acoustic group related to the Adif-Bois project. And I've seen some of them are here today. Okay, so what is the problem concerning the impact noise is that we need to improve the occupants' acoustic comfort for lightweight floors. And in the last housing certification by Qualitel, CERCAL, we are imposing a new impact noise requirement, and the LPRAM NTW and LPRAM NTW plus CI 52500 has to be below 55 dB. Okay, maybe I should add that for the French standard regulation, we only have a requirement on LPRAM NTW, and it has to be below 58 dB. So the question was, how do we reach this performance, especially regarding the low frequency aspect with the adaptation terms dealing with the low frequency. So if then we look at the performance of the floor, we decided to look for floors that had a performance between 50 to 52 dBs in terms of LNW and LNW plus CI 52500. Oops. And one of the potential solutions that we thought about was adding a weighting layer to the floors that we usually deal with. So in this presentation, we will have a different type of wood floors. The first one would be a wood frame, I would say standard floor. The other one is today a more common, it's a CLT floor. And then the last one, which is a Jean-Luc investigation, concerns a box type floor. So for the wood frame floor investigation, we started with a basic floor that we developed in the Acoustics, the French project dealing with the wood walls and floors and buildings. So here you can see an image of such a floor. It has like a suspended ceiling and mineral wool in the cavity, and then one floorboard on top of the joists. The idea was to use a dry floating system on such floor, and we used a standard floating system, which is composed of 2 layers, a 10mm rock wool layer and 20mm fiber reinforced board. Okay, we're trying to develop something which is all dry. No pouring concrete or anything like this in these solutions. So we decided to use a modeling approach to try to find what was the minimum weight we needed to add to this system in order to reach a chosen impact noise performance. So in this work, we used an optimization model, which is based on genetic algorithm. Such algorithms are based on the notion of natural selection that are applied to a population of potential solution to a given problem. So we approach the optimized solution through successive jumps. Okay, in this case, we use a population of 10 individuals, and we use 10 generations of this population in order to find a converging solution. And for the cost function, we use the global index LNW plus CI 52,500 minus the target. That was the cost function we were trying to minimize. On the right-hand side of the slide, you can see the different generation are different colors and forms. Hello, somebody's talking at the same time? Please. Thank you. Oops. So here you can see the convergence of the system. You can see that after the 5th generation, we have globally a good conversion for the solution. So our parametric study involved the thickness of the weighting layer from 10 to 60 millimeters, variation of the density from 1,000 to 2,500 kilograms per cubic meter, as well as the variation of the elastic modulus. Okay. After we did like several optimization procedure, we found out that the weighting layer had to be approximately 70 kilograms per square meter in order to achieve the targeted impact sound level performance within a 2 dB margin. We chose to have a 2 dB margin to take care of the material properties variation as well as the modeling uncertainties for such floors. So after we define a solution, we looked at laboratory testing, and we did test 3 different configurations, and we tried to find weighting layers easily found at the store. So the first type we had was the concrete outdoor tiles, and they corresponded to a density per unit area of 82 kilograms per square meter. And they show here on the picture, on the top picture. So they were applied directly to the floor. Then we also use solid terracotta bricks. In this case, they are a little bit heavier. They correspond to 100 kilograms per square meter. This is the picture on the right. You can see a brick right here. And finally, we use the gravel mix. We use the 50 millimeter in thickness layer, corresponding to a density per unit area of 78 kilograms per square meter. And you can see here the person trying to get a homogeneous layer and finish it before putting the floor on top. So these are the performance that we obtain in the laboratory. So you can see in pink, the basic floor performance. So of course it's really high. So, it's not really interesting. It's just for comparison. So for configuration 1, which is the concrete tiles, 82 kilograms per square meter, you can see that the solution is reaching the targeted performance. We get a 49 dB LNW plus CI. And when we add different type of floor finishing on top, either a PVC, a carpet, or a parquet, we remain in the same range of performance, just below 50 dB. Okay. If we look at the configuration 2, which corresponds to a heavier weighting layer of 100 kilograms per square meter, obtained with the terracotta bricks, you can see the performance is a little bit better since we're adding more mass to the system, with and without the floor finishing. And then finally, the last configuration corresponds to the gravel mix, 78 kilogram per square meter. And you can see we achieve really good performance, better than the first configuration, correspond to the concrete tiles, which are about the same, mass per unit area. Okay, so, in conclusion, to achieve our performance, we need a weighting layer of about 80 kilogram per square meter. Here I show some measured results in terms of spectrum. Here I only show the measured values for the different configurations, but we had fairly good agreement between the measured and the predicted results. Okay, you can see that the configuration 3 that corresponds to the gravel mix, you can see a very good performance from the, starting at 200 hertz down to the higher frequency compared to the other ones, but it does perform a little bit less good in the low frequency range at 50 and 63 hertz. Okay, and the first configuration had a higher level at 125 hertz. On the right-hand side, you can see the impact sound improvement related to the different floor finishing that we put on the system. And one has to be careful because you can see that the performance of this floor finishing is different as a function that the system we tested. Okay, so we cannot generalize the performance of the floor finishing. For example, you can see that the parquet on the floor configuration using the gravel mix is really low in the high frequency range. It's even below 0. Okay. So next we'll go to CLT floors investigation. I don't know if Nicola is here and wants to take the lead on the talk, or if he wants me to keep on going.
No, just go ahead, Cathy.
Okay. So we carried different, another investigation on the CLT floors, and that was done under the Adif-Bois project and financial support. So we are testing a CLT, which is 140 millimeter in thickness. And you can see a picture here of the CLT floor mounted in the laboratory. And based on this CLT floor, we tested more than 20 configurations. We tested the system with and without suspended ceiling, with or without added mass layer, with or without floor finishing, either with a standard floating screed, which is a humid mortar-based screed, or dry floating screed. Okay, here in the middle you can see one of the system with the gravel as an added mass layer, and on the right hand side another type of floor where we had a point contact and a concrete screed on top. So we tested a lot of different configurations. And I will only show a few results. Hopefully, most of the results will be available very soon for sharing with everybody. So these are the results for the CLT floor investigation without ceiling, because one of the requirements was to try to find a solution with the visible wood underface. So we try to find a solution, and here is the solution with the gravel, 106 kilogram per square meter, with a standard floating screed on top. Standard, which means cement-based for me. And here you can see on the right-hand side of the screen the description of the different layers. So if you look at the results, if we have the gravel with the screed being on a 15 millimeter thick mineral wool, in terms of impact sound, we obtained 54 dB when we include the low frequency range in the performance, which was not enough, which was not meeting our targeted performance. And if we added the plastic floor covering, we actually reached the 52 dB performance, which was our targeted performance value in this case. Another system that did fulfill the requirements was the concrete screed placed on point elastic support with sound absorbing layer in the cavity, which correspond to the picture you had here in the previous slide. So in this case also, without the floor finishing, we were at 54 dB in impact sound performance, including the low frequency. And when we did put the plastic floor covering, we went down to 51 dB, which is relatively similar to the previous system. I haven't mentioned, but of course we measure the airborne sound insulation from this system, as well as the impact sound related to the rubber ball. But in France, we don't really have a target value for this impact sound with the rubber ball. So these are the two solutions we define without using a ceiling. In the next table here, you can see solutions we have with ceilings. All the ceilings use 100 millimeter distance between the underface of the CLT and the suspended plasterboards, and incorporates 80 millimeter of mineral wool in the cavity. Okay, so we have a solution with a screed, which is a dry screed, if I remember right. Nicolas, I think that's correct. And we had the ceiling was made of two standard plasterboard, 13 millimeter in thickness. But again, in order to reach the desired performance, we had to consider the plastic floor covering. In that case, we reached the 50 dB impact sound, including the low frequency aspects. The second one concern this system here. What we had we had a honeycomb system, which is in, I didn't put the thing in the right order, but okay, which is correspond to the lower part of the table here. And of course, in the honeycomb layer, we added beads or mass to the system, and we use two plasterboard of 18 millimeter in thickness in order to reach the performance. Without or with the floor covering, we reach the performance in this case. And the middle part of the table correspond to a screed with a thin resilient layer with a ceiling of two plasterboard of 18 millimeter in thickness. And here we tried it with a plastic floor covering as well as with tiles. And we can see that the system with the tiles glued to the floating screed does not meet the requirements. Okay, only the plastic floor covering allows us to reach the target. So for the CLT floor investigation, we have a low frequency effect observed in relation with the floor finishing, or the floor finish covering. And we did not expect this because usually we try to find a solution without the floor covering. And we say the solution is fine for all floor covering. So we have to be really careful with this floor finishing. The plastic floor covering finishing implemented was associated to a low frequency improvement when we mounted it on the standard screed, and to a low frequency deterioration when it was mounted on the dry screed. Okay, for the tiles, we had a low frequency deterioration, and that's why we didn't meet the requirements when we use stars on such floors. Okay, another remarks regarding this investigation was that the weighting layer, when we used the gravel mixed, we did meet the requirements in terms of performance. However, when we used a mortar-based weighting layer, which means it's a bounded system, then we didn't meet the requirements. So one has to also to think about this solution and whether use an unbounded granular material rather than a mortar-based screed for weighting layer. Okay.
Hello, Luis, do you hear me?
Hello.
Okay.
I can hear you. You have a question or? Okay, the last part of the presentation is concerning box floors investigation. So Jean-Luc, if you want to take the lead here, since
if you want, but
it was most
anyhow
the only one who participated in this.
Yeah. So I will do it very quickly because we are going out of the time. Huh? Okay, so this is some results coming from some tests since we did other with the same building system. Again, this is a development that has been done together with Mesa Wood, and the target of this company was to create a very high level performance floor with a big cavity using less wood. And so they are using LVL, and their market target is something like in between 8 and 12 meters of span, or 6 or 12, 6 and 14 maybe. Okay, so we tested some different configuration, and it's inspired more or less by the Belgium bunker floor. Thank you, Belgium people. This was during the Woodrise Congress in 2017. The Bartingelare presented some results, and Mesa Wood said, "Oh, this very interesting. Why don't we also use this system?" Okay, so the building system is a reversed floor, and the studs are on the top, and inside the cavity it's filled with a little bit of gravels. On top of it you have insulation material, and then on the beams that are on the top, okay, so the beams, you have beams, and then you put a panel, okay, on that panel, in between that panel and the beams, you have to put some elastic layers. Very interesting system in that case. And on top of this, you can put a cement floor topping. So maybe we can go direct to the measurements. A very interesting thing that we identified, but this was not actually our purpose. The results were strange, so we said, "Oh, where is it coming from?" And then we noticed that there was screw inside the floor. So the people, when they prepared the floor, they just put a screw because they couldn't imagine that you cannot put a screw on top of a panel. Okay, so structural behavior of the floor is taken by the bottom part of the panel. Okay, the bottom top of the box, and actually it's fire resistant also, the system. So we don't need that screw. So, but anyhow, it was there, and look how much we can gain from that result. It's something like 10 decibels. Oh, I see that we don't have the low frequency of results of this, but never mind. We have it and calculate it. Okay, and we also when we put on the top of this floor a floating screed, it's a lightweight floating screed. Then we are, you can see, very good in low frequency behavior and also in impact noise. Okay, so we also made some measurement. If you can show the next slides, we make some measurement to create a model to calculate and derive from measured results derive calculated results. And we are showing here the curve of this calculation. So when you add a ceiling on such a system, then you also enhance the performance of the floor, but not that much. Okay, and if you use the cement screed, of course, you enhance the building performance. That's it. And this has been done using calculation. That's it. Is there any conclusion on that work? Yeah.
So no, it's just a general conclusion. We're
So
looking at different type of wood floors. We have different solutions to which are targeted performance that do integrate the low frequency range with respect to impact noise. And we use a mix of laboratory tests and modeling approaches, which allowed us to optimize and evaluate before testing in the laboratories the performance of a system. And of course, the weighting layer appears to be appropriate. But one has to be careful about the type of material we use as weighting layer. Especially that's what we've seen on the CLT floor. Okay, and also care must be taken regarding the floor finishing effect. And that's all for today. Thank you.
Thank you, Catherine. Thank you, Catherine. Yes, so we are a little bit late on our schedule. And now we are going to give the floor to Klaas. Klaas, are you here?
I'm here. Do you hear me?
Perfect.
Yes.
Ah, super. I will try to share my screen then.
Yeah.
Okay.
I continue. I think it's working. Okay. I don't know if I have it in a full screen mode or not, but it should be okay. Thank you very much, and interesting start. And thank you for organizing this session, because I think it's quite nice, and it's important that we share this kind of knowledge between countries. And I will give a brief overview of what we are doing in our small company. Ongoing projects and experience from the field in wood projects. We are now we're still very small. We are 4 people now working in the company and based in Malmö in Sweden. And also in the north, we have 1 office. So we have our commissions are to, I would say, 98-99% only wood. Several stories in wood. So it's a hot topic in Sweden now. Now. So the content of today, ongoing and recently finished projects, results and future challenges. I will go through some CLT buildings with, I call it traditional CLT. Maybe it's not, I don't know what is really traditional CLT, but it's more like plates that you put together. And at least in Sweden now, it started to be very hot with volume elements in CLT, prefabricated in factories. And we have also lightweight joist system, of course, flat elements and volume elements. I will not talk too much about volume elements, but we are involved in some projects with volume elements with joist system also, but I have limited times, so I think I will stop there. And I think it was quite interesting to hear Lin Hu before, because all this problem with predicting sound insulation, I think we need to understand much more still to predict. We are a little bit working in the blind. So you have to be a little bit stupid to do this. This is a summary of the projects I will show you today. This one It's one of the biggest projects we have for the moment. I have been working with it for 4 years approximately. It's in the city center of Stockholm. It's 13 stories of wood in CLT, 4 buildings, approximately the same. It's called Cederhusen. The second one is volume elements in CLT in Nyköping, close to Stockholm also. And they're not all finished, but main part of these are finished and already moved in. So they are. We have seen how it's working in the reality. I will come back to that. And this house is in Karlskrona, south of Sweden. It's a quite fancy place and very nice project. And if I go down here, it's student dwellings in Örebro. And here we have some I-joist systems in Skellefteå in the north of Sweden. And this one is an 8-story building in wood joist system in Enköping, a little bit east of Stockholm. So if I continue now with the first project that I want to show you is this Cederhusen. The first house out of 4 is now built. They haven't moved in yet. We are doing regular controls in this building. And it's fully in CLT. There is there is some concrete on top here, as you see on the floor structure. But all the stabilizing elements and all the elevator shaft and everything is in wood, CLT elements, nothing else. So it's quite a lot of potential flanking transmission paths and so on. Because also it was quite rough requirements to really keep a lot of, don't make it too thick, as they say, because we need to have enough space to rent out. You can always improve by adding layers on the side of the CLT panels and reduce the flanking transmission, for example. But the final solution in this project was to have a concrete slab on top, or rather a CLT slab as a bearing element. And they vary from 160 CLT up to 220, depending on the load and the span and so on. And then there is a 30 millimeter of impact sound board. And then we have 80 millimeter of concrete with floor heating. And then there is parquet on top. And we have a ceiling to both manage to fulfill the requirements, but also to hide all the service equipment in the building. And this is actually not a solution that is not, the builders are not very happy to use it because they don't want to work from below. They prefer to put all the installations on top. I will show you some other examples later. But in this case, it was not possible to do anything else because the house needed to have some load in order to stay where it stays, because otherwise it would blow away. So it was a requirement due to have some specific weight, 300 kilograms per square meter for the floor approximately. And then we have the junctions, which is first the structural engineer, he didn't want any interlayers between the different stories. But at the end, we managed to convince him that we need it, even if I'm not super convinced that it's really needed, but we are looking into the results now from early studies. But there's only 6 millimeters of rotoblas interlayer here, xylophone, nothing else, because the static designer, he didn't manage to, or she, it was a girl actually, she didn't manage to calculate the stability with too much interlayers, and it's also tricky for them to predict what is the consequences. And the requirements in this case was to fulfill what we call in Sweden sound class B for impact sound, which is L prime NTW plus C50 52 dB, and DNTW plus C50 to 3150 is bigger than 52 dB also, and that is the minimum requirements. And said at an early stage, we cannot go higher because of the flanking transmission paths is so many. And I will show you some initial results. This is from inside the building. At an early stage, we told them you have to build a test room, which they also did, with not the real concrete in this case, it was plates, 80 millimeter thick, on top of a impact board, and then floor covering. And they made a ceiling in the floor below also. And we took the worst case scenario with 4 walls, flanking walls in the room, not covered with any gypsum or anything yet, just to be sure that we were on the safe side. And the results from this test measurement was impact sound 44 dB, super good. Better than expected actually, better than predicted also. And airborne sound was more or less like predicted, 53 dB. A little bit better actually. I was thinking with this thin layer and with a wooden, visible wood, it would have been a little bit worse. And this here is the result from airborne sound. And the different colors here is, the red one is the measurement results. The gray one is predicted. We adapted the model after the measurements also to make sure that we're on the right track, to be able to calculate more rooms and other configurations. And this yellow one is the transmission calculated with only the floor structure. So we have almost, if this is true, almost everything is going through the floor structure. The second project, or the second, third, and fourth, and fifth project that was finished last year actually. This project was finished October. And this was finished 2019, and this was also 2019. And this was also in November, December last year, so it's quite recently. All of them are built by volume elements. So this is a junction. This is one volume, this is another volume, and this is the third volume, and this is a fourth volume. So it's just a junction that you see in different rooms on each place. And this CLT plate is approximately between 140 and 160, depending on the shape of the flat and so on. This CLT in all cases are 100 millimeters. The space between the CLT differs depending on if they have if they are covered with a gypsum board or not on these sides. And this is a raised floor called Granab in this case. It's a pre-manufactured floor by a manufacturer in Sweden. 22 millimeter particle board and 1 or 2 layers of gypsum and then parquet on top. It differs a little bit from project to project, and this cavity here is around 180 millimeters. And this plate is between 80 and 100, or 60 to 100, I would say, depending on the system. So there's double CLT here actually. And there's an interlayer here, 25 millimeters of resilient layer. And then you have to connect it depending on the height of the building, of course, which is very difficult to predict. How much does that affect the sound insulation at the end? The results from this project shows approximately, we have the requirements first, it's BBR, which we call the minimum requirements in Sweden, the legal requirements. It's like this, that you have to be lower than 56 dB for impact sound and higher than 52 dB for airborne sound. And like in this case where you have gypsum on all sides, you have gypsum on the ceiling and gypsum on the walls, one layer, and the spacing between the volumes are 80 millimeters in this case. Then you have around 54 to 55 dB in impact sound and 53 to 54 dB for airborne sound. And quite stable between different dwellings. it doesn't deviate too much. It's around between, I would say, between 51 to 55 dB, depending on the size of the rooms and so on. Sorry, I go back again. If you have visible CLT, like in all these cases, we have visible CLT, 100 CLT, 100 space, 100 CLT. Then it's a little bit more spread in the measurements. I don't know why it's, but I think the gypsum helps to smooth out the results a little. So we have between, I would say, we fulfill the requirements, but it's not more than that. It's just on the limit. It can be actually a little bit lower. So we have plus minus 4 dB, I would say, in these cases. So it's a little bit too much, to feel good when you go to sleep. Another project, which is very typical way to build today in Sweden. I see here now this is Swedish. I'm sorry for that. I will try to explain in English anyway. This is the separating wall between apartments, fire gypsum, OSB plate, and then acoustic profile, and 10 millimeters of wood lath, and CLT, 15 millimeter of airspace, 95 millimeter of joist and isolation, and 2 times 13 millimeters of gypsum. And by using this, the different, we didn't need any xylophone between the layers in or xylophone or xylomere or whatever between the different stories. Since we have this covering to reduce the flanking transmission in both ways. And however, in the facade, there was not visible CLT because there was one gypsum mounted directly on the floor, on the wall here. So it was, but still no other layer to reduce the sound emission from the walls. And the floor is built up again with this granab floor, raised floor called granab. And we had on top of that 22 millimeter particle board, 2 times 30 millimeter floor gypsum, particle board again for floor heating, and then foam and parquet. And there was also a ceiling here on resilient layers because of they had continuous CLT between the different dwellings, and that's why we needed to reduce the flanking transmission through the CLT in the ceiling. And if we had visible walls inside the different dwellings, which was not separating between apartments, we had a layer of 25 millimeters layer between here to secure that it would be not too much transmission this way. And it's, as you can perhaps assume, it's a quite nice location of this building. It's fantastic, actually, close to the sea in the archipelago of Karlskrona. Requirements was to fulfill sound class B, 52 dB for air impact sound and 56 dB for airborne sound. And we did quite a lot of testing, and we managed almost 50, 60. We managed, but there was few exceptions here actually. For example, here 58 minus 7. It's a little bit too bad. It's even not BBR. But it was a very small room, and small rooms are tricky to fulfill, no matter if it's I would say concrete or wood or whatever. But the mean value in all measurements we did fulfill 56 dB. And in Sweden, it's okay to have 56 dB if the deviation in single measurements is not bigger than 2 dB. And impact sound. Sorry. we had a mean value of 52. It sounds almost like I'm lying because it's just spot on, but it's true. Yet again, it's so we were spot on here. And we made I show another example of a project that's moved in also, is Sjöstadsorangeriet. It's exactly the same build-up. The only difference between Sjöstadsorangeriet and this Kihlströmskaj in Karlskrona is that we had a floating gypsum on the top of the granab floor, and we were thinking it would be the same, but the result was actually a little bit worse. We fulfilled BBR, the minimum requirements in Sweden, but not the sound class B for impact sound. Airborne sound was no problem. And then I move to the next project, which is Karlgård in Skellefteå, and another one, Sankt Iljan in Enköping. It's flat elements prefabricated in a factory in the north of Sweden, but produced by I-joists. And the requirement or the ambition for this project with 5-point houses was to have less than 48 dB sound class A and bigger than 60 dB in airborne sound. It's a very nice company to work with because they have really high ambitions and they put the limits quite high. And they build everything in a dry environment. So they build the elements in the factory, and then they use tents. This is the tent for these 5-story buildings. And in Enköping, they have an even bigger tent because it's 8 stories. So everything is dry and it's very nice conditions for the workers. And they have a flow of material coming in time from they have a very nice flow of the material from the factory to the building site. So it's an efficient way to work. And they actually fulfilled sound class A 43 dB with a very light structure for the floor. And the key is here to use just move my bar a little here again. They're using I-joist here in the floor structure, and then there is a stiffener I-joist also in the other direction to make the floor much stiffer, and they are connected by a beam under. And then there is a LVL board here, glued and screwed together with the beams, make it even stiffer. And then there is a floor heating board here, and then parquet on top, nothing else. And to make it possible to transport these elements from the building site, from the factory to the building site, they use a spring, steel spring in the ceiling, which can, when it's transport lying, it's just lying directly on the together. And when you lift it up, the spring is starting, the ceiling is falling down. And everything is prefabricated, even this installations and everything is prefabricated and designed first in the 3D model. And they just plug it together in the site. And the junction is also a specific junction that I'm not allowed to show, but there is a hanger, specific hanger, also in a steel spring for the floor, which means that you have quite a lot of flanking transmission this way. That is also why we don't fulfill sound class A in the vertical rooms where you have 1 or 2 flanking walls. So we have 58 dB as a mean value for airborne sound, but it's due to these flanking elements that is going, because you need this to carry the load for 5 stories. You cannot cut it between here. And the impact sound is 43 dB, which I think is extra. I was there to measure and it was quite fantastic actually. And the other project with 8 stories is a little bit less good. It also, they have made some savings in this project. It's not, we have different types of, the first project is like people are buying the flat. bostadsrätt in Swedish. And the other one is rental flats. So they try to save because the margin is less good. And they made some savings, but still we are fulfilling between BBR and Sound Class B. And when you have this 8-story building, they had to put a bearing wall straight through the building also to make it stable, which complicates the sound transmission quite a lot also. Conclusions. I hope I am in time. First of all, I think elastomers and their effect on flanking transmission, stability, and they need to be further evaluated. It's a very high cost in projects, and if you just gain 1 or 2 dB, maybe you can reduce the requirements instead a little bit. I don't say I know it's true, but it has to. We have to know more about this. And high cost, it's. I had an estimate from the people working in Cederhusen. They said around 1% of the total project cost, and it doesn't sound much, but if it's a project cost of 200 million, it's 200 million Swedish. I mean, in this case, it's not as much, which is 20 million euro. It's like 200,000 euro just for the elastomer to put it in place. So if we can do something about that, I think they will be super happy. CLT volumes with visible wood is tricky to predict. It's really not easy, I would say. And now the higher the building, it becomes worse. We're working on 3 8-story buildings with CLT modules now, which is will be interesting to see how we can connect these different modules to make it to feel good. Gypsum covering, even if they are directly mounted, gives better and more stable results. It's not you don't get as much spread in the results as if you have visible CLT. And I would say it's possible to achieve very high sound insulation with I-joists. And it's also a good system to really reduce the amount of wood to use, or rather you use the wood in a better way, I would say, because it's more efficient way to use wood. You reduce the amount of wood, which could be good if you really want to build a lot. And flanking transmission in bearing walls limits the sound insulation, but it's still acceptable. So I don't think it's a big problem. And I think that was what I wanted to say. Thank you.
Thank you very much, Klaas. Yes, you were ahead of time. I mean, you are 5 minutes late, but it's okay.
Yeah, you accept it.
Yeah, it's okay. Okay. Well, we will have some question. I have some question for you later. Now I have to share my screen. So
I stopped to share that.
Okay. Yeah. And here is my presentation. Yeah, that's good. I think you don't see the same thing than me. Huh? I hope so, huh? Because oh, here. So now I'm going to talk about the project we're working now. I would say it's the biggest project on acoustics in the area of flanking transmission. Today we are now preparing a special laboratory for that. This work started since long time. Actually, there is a French non-profit organization that tackled all the problematic of building with wood in multi-story building, and they had to answer all technical, but not only technical questions. And this non-profit organization name is Adif Bois. So they had major big projects for that, and Acoustic was one of them. So last year we answered we participated and then answered to a big call of this non-profit organization, and we grouped together with CSTV and CERCAL to prepare what we call maquette acoustique à Divois. And this is done for measurements of flanking transmission and also prediction of flanking transmission in wooden construction, in CLT wooden construction. Voilà. So all the team is around the table, I think. We're still here all together. Cathy is working, Nicolas is working, but also I saw and heard some of the experts on acoustics from France. Okay, I was complaining about time, but I don't know if, yeah, I have to measure also my time, huh? Okay, so this is the maquette acoustique. I don't know if you see the title because I cannot see it, but maybe you can see. Can somebody confirm that? Yeah, because the line is eaten.
We can see it.
Okay, thank you. Okay, so this is the mock-up or the maquette. This mock-up is made of 3 floors of CLT and also walls made of CLT, and all surrounded with stud walls, say, framed walls, okay, facade. So here you have the picture of how it was last week. So we started this in November 2020, and it started, of course, with concrete, and we had to prepare. The soil here is very weak, so we had to make some pillars, and we built up a very simple structure, concrete structure. On top of it, we prepared our maquette, our build-up. Here you can see the first part of the building where you can see the cross junction, horizontal cross junction that we're going to analyze, of course. And here we are. It goes very quick, actually, and it, all together, when the wood starts being implemented, it only took something like 7 days. Yeah. So so this was very quick, and here you can see some picture of what was here last week. So you can see here sun actually in the window here, but it's a false information, huh? Because while we were implementing this building, it was raining all the time. So that's why you can see even the wood has been really in contact with water. So that's why we also now need to wait a little bit. Yeah, we can see that in Sweden you are using tents, but this is not at all something usual in France. So we are not using tents, as you can see. So our building, our maquette, I will say it in French because it's the name we gave it. Our maquette is going to be used for a flanking transmission measurement on junction. And of course, our junction are varying from different part of the structure. So we are going to make that flanking transmission measurement on the structure, the naked structure. That means that only CLT is going to be measured here. Bare CLT connected with other part of CLT, and also bare CLT connected with plasterboards, plaster board walls, huh? And facade. Also, we are going to make some facade. Also, to make it a bit more, it was the occasion to work a little bit deeper into our knowledge. That's why we also change a little bit the plan of experiment, and we added some things to identify. And here we are going to identify the point connection So what we ask the designer is to let us the system with different with the capacity of changing the point connection. So here where you see the dotted lines, we are going to change the connection between the floor and the structure. Okay, so we are going to start with actually no screws, then a screw every 500 millimeters, and then screws like it should be 250 millimeters. So 3 steps of point connection, and this is to identify the performance for 2 things. One is the point connection knowledge, point connection modeling, and also the point connection together with resilient layers. Because on the first floor here, I don't know if you see my arrow. No, not even me, I don't see it. Oh, here. On the first floor here, the panels are lying on resilient layers. Here you can see the resilient layer. But first, let's talk about the envelope. The envelope is a facade. Facade is not it's not a structural bearing system. It's only facade that is hanged on the structure. The structure is the blue lines here. It's the poles and beams that are making the structure holding of the construction. And of course, the CLT in the cross here, cross in the first floor, half cross here, and only 1 panel on the last level. So the building system, I was saying that it is different from part to the other of the construction. First floor is with resilient layer. Here you can see them. It's the red line. Okay, and on the second floor, it's the same building system without this resilience channel, okay, the resilient layer. So this will help us to better understand what is the influence of this material, of course. And then here we have on the edges, you can see the structure holding the floor. Okay, it's a pole and beam structure, and the facade that is only making the box all around it. Of course, it's going to be doubled with plasterboards, and this is going to be done in the near future. It's going to be start in 2 weeks. Okay, so today the structure is completely finished, and it is ready to follow up, but we cannot close it because it was a little too much humid. Okay, so after it is going to be doubled, I mean the envelope is going to be doubled with plasterboards. The lining are going to be put on the facade, and then we are going to build up the building system. So we have 2 parts of the structure, and this is vertical. One part will be dedicated for visible wood with, let's say, system on the top, okay, performance system on the top. And of course, this is a lot inspired by what Catherine showed you a little bit earlier. The building system here has been tested in the laboratory at CSTB. And so one part is with insulation from the top, and the other part is more usual building system with CLT floor, 140 mm, with a floating screed on top of it, cement screed, and ceiling underlayer, ceiling underneath, so a suspended ceiling with 180 millimeter gap. So after we build up everything, we're going to make a huge quantity of testing. After flanking transmission, we're going to make all possible tests in all direction for airborne noise, and also from one room to the other, from top to bottom, and also diagonal, of course. And this we are going to do it for airborne and also impact noise. And after we make this first investigation on building system that we believe is going to work on this structure, we are going to change the build-ups. So we are going to work on wall with visible wood and make all kind of permutation inside the building system. Altogether, we're going to perform something like 40 tests for impact, more than 50 maybe, and for junction, I have I have it in mind. It's something like we're going to measure something like 16 kind of junction in KIJ. So it's a laboratory for testing and measuring the KIJ and also validating the system complete system. It's an in situ measurement laboratory that is controlled. So it's a laboratory, but in situ. Okay, so so to have an idea of what we're measuring, just look a little bit of how much time I still have. Not much. So I'm going to run through a study that I prepared together with Woodrise. This was a few years ago. We worked together with people from Technalia on that. So we measured some flanking transmission, and this is going to be more or less our, well, I would say we don't have much information about flanking transmission with CLT, and this is part of what I have, and I am of course very interested if anybody can help in sharing the information he has on flanking transmission. So we did some flanking transmission. This was 5 years ago. It was presented at Internoise in 2018, I think, yes. And so we worked on different measurement, and we worked on in situ measurement. So in situ, you have to do everything in one night, actually, because during the day, the people are working on the site, and they will not wait for you to make some measurement, you know. So we worked on Beard CLT, and also we worked on facade and cross junction with doubling, with all the structure and even the plasterboard. So this is how it looks like, and this is how we measure, and this we are going to see. See, again, a lot of water. This is exploitation of measurements. It's a lot of measurement, of course, and exploitation. And here are some measurements of coupling and dumping. And this is physical measurement that we can use to calculate the KAG, that is the factor de réduction vibratoire, vibration reduction factor, something like that. Huh? Okay, so here are some results on Bear CLT. This is what I have. I have maybe one or more building system, because during that project we measured some flanking on different structures, and you can see here some results. This is also has been measured on CLT with different thickness. This was very interesting also to see what is the difference and so on. And we did that also with wall that are already with their own linings. So here, let's say if you are talking about flanking transmission, the level of performance of a complete structure is very high. And actually what we noticed when we made the testing, validation testing, is that, well, flanking is not that much influencing the results. And here we proposed to make a wall. It was a little bit risky because part of the structure was open, and so you can see the walls, and this is you know, each level has its own wall visible. And when we made the measurement, it was okay. for the regulation, the French regulation. That's it. So now for our project, I'm going to show you the video of the full story of how we performed that work all together. If the machine wants me to do it, let me see here, maybe. So, oh, let me see it. Actually, it took so much time, this one, compared to the regular fabrication. It's a 100 square meter per Here you can see everything, and even downtown and so on.
Hein?
Resilience layer that for the floor. So now you can see it on the top. Huh? All junctions are not here. Huh? Now they're so they had to change part of the panels that were broken and so on. So now they are nearly finished. And, well, this is the boss, huh? He's the owner of the company. He was there every day. Having fun.
On voit juste ton ombre et on comprend ce qui se passe en fait.
Ah. Last floor implementation.
We don't hear you very well, Jean-Luc.
Oh.
Speak louder, please.
Yeah. So this is the last floor implementation. This is a little bit accelerated, and the noise that you're going to hear is not the right noise, huh? It's not the right noise. Implemented. This is the last I had the privilege to put it on the top of the building. Thank you very much. Of course, we all wear a hat and mask, of course. So this was last. Now we'll go back. Okay, thank you for your attention. Oh yeah, this is. Oh, and of course, they finished the ceiling. Et voilà. That's it. So Oh, now in a very dark ambience. Huh? I didn't notice. Yes. So now it's time for everybody. We're still here, all around the table. Thank you for listening to us. Now I think it's time for us to answer your question. If you have question, or open the debate. Maybe we can open the debate on, I don't know. Yeah, I have a question actually, if you permit, unless somebody want to ask a question very quickly.
Well, there were questions during the presentation, so in the chat, so maybe we should go through these first.
Okay, then. Okay. I cannot see it.
Well, okay, so I'll check. What were the properties of the resilient layers? Were they different? That's for class. The properties of the resilient layer between the different modules, or were they different at each level?
Yes, they are different on each level. It's adapted to the load, the quasi-permanent load.
Okay. And another question, I guess it's for you as well. Did the sound insulation vary with the height of the building? I mean, the first floor was worse than the 7th.
No, we haven't seen that actually too much in these modules, at least.
Okay.
So, but in other projects, I know that there have been some differences. But for the modules with CLT, we haven't noticed that it's a big difference.
Okay, and we've got another question for you. Did you look at the frequencies below 50 Hertz?
In some of the cases, yes. We have measured down to 20 Hertz, but I don't have it in my presentation, and I have to dig for it in this case.
And so do you remember what it looked like? Or?
I think I had it in one of my slides, actually, the C from 20 Hertz, like the one that we are using sometimes in Sweden, just not by legal requirements or anything, but just to evaluate.
Okay, get experience and data.
It is.
Okay.
I can send it afterwards to anyone who wants. Just contact me in this case, I will.
Okay. I think I went through the list. Maybe the people that asked the question, if I didn't ask them correctly, they can. Somebody say, how do you measure at 20 Hertz?
Yeah,
that's a good question.
Yeah, it's a good question. There is no standard for that, so we don't compensate for a reverberation time or anything. We just measure the level.
Yeah, you just measure like you do standard measurements, and you just look at 20 Hertz. But
yes, not perhaps. It's more to collect data, not perhaps to see some pattern. But actually, we are more in all these CLT buildings. We are more concerned about the airborne sound insulation than the impact sound, because of it's more tricky to fulfill, and we have more problem to fulfill it. I don't know if it's a more problem, but it's the requirements perhaps is not perfectly adapted to CLT buildings.
Okay.
One question to Klaus to complement that. You mentioned that it's difficult to fulfill. Is it the national requirements that are more difficult to fulfill, or is the experience of the tenants of the buildings that is more? Yeah,
the experience of the tenants, I think it's okay. They think the national requirements are good, but sometimes there's requirements of sound class B, and then it starts to be tricky to fulfill. But I don't think it's always needed to make people satisfied. Depends, of course, on which type of dwellings and how big they are, and if there is a lot of different. One thing that could be very interesting to further study, I think.
So you mean that like tenants can be satisfied with the airborne sound insulation, but still we don't fulfill the requirement?
No, you have to fulfill the requirements. I think you need to have 52 at least.
Okay. Thanks. Thank you for me.
Any other question? Or subject you want to talk about? Or information you want to tell us? Incredible measurement you made, or or sharing of flanking transmission to me?
Only to you.
Only to me. To everybody, I mean, around the table. Huh? No?
I have, if I may, have one question to Catherine. About you presented that on, I think it was on CLT floors, when you have different floor coverings, you got different values.
Mm-hmm.
Yes, but have you also really implemented that and seen like how it influences the impact sound we perceive in the building? If it really influences, or if it really makes a big difference in the impact sound insulation?
Well, if you look at the index, which is the LF max, which is related to the rubber ball, which I would say it's relevant to what people feel in the building. I'm not sure. Then the floor covering doesn't affect very much this index.
Okay, so even though we get different values for Ellen, but still we don't get much difference in the experience.
Exactly.
Okay.
So we'll see on the mock-up what we get and have a real feel for it, you know.
Okay. Thank you.
Yes.
I think it's good that you have built a real mock-up with several stories. That will be interesting to follow.
So on that, I have to tell everybody that we have that mock-up. We are not going to destroy it just after some measurement. No? So this mock-up is here for I think minimum 5 years. Our idea is to use it for research, of course, but also for industry. Why not? We have already people that are coming through Adivbois, the non-profit organization, asking for time and space for measurement. You know, so we are happy to use this new facility. And even we are thinking about using it also for vibration. We're thinking about using for assemble, disassemble, and so on. So we have lots of projects that are linked to this mock-up.
Is it located in Bordeaux? Or?
Yes, it's just in the back of the parking.
Okay.
You know, you have been here, huh?
Yeah.
So it's in the back, just in the back of the yard. And actually, we have even more land. We can build up other demo building. We can consider this like a demo building also. Yes. So and I think we are going to build up more demo building. Yes.